Physics 101, work and energy homework number 2, problem number 10 is the donkey problem. Lots of people have trouble with this one because it's a little more complicated. We have to deal with a third dimension. We don't just have x and y, we also have an incline, so it's going up as well. We have a donkey pulling on a cart, and the rope makes an angle labeled B here. With the track. So the direction of travel would be this way, and the donkey's force is that way. And it's also on an incline, so he's going uphill as well. So we have essentially two different free body diagrams. We can look at it from the side view, where you have the hill, and the cart, and the donkey. And we have the forces, the force that the donkey's pulling. We have gravity pulling down. We have friction holding back down the hill. And you have the normal force at an angle. Now, 3 of those are not on my standard XY coordinate plane. So instead, I'm going to redraw it so that it's flat. And I'm not changing anything, but I'm just drawing it in a more convenient way. I'm changing my coordinate system to be more convenient. And looking at it now, you got the donkey force, the normal force, and the frictional force all on the XY plane, and the only one that's not on the XY plane is gravity, and it's making our angle angle A with the ground. So this angle here is angle A from the drawing. That's this one right here. Let me label these real quick. So we have, this is the force the donkey is applying, this is the normal force, this is force of gravity. So then we have Fgx, and we have Fgy, and then we have force of friction going that way. Cool. Also, if we're looking at it from like a top view, from a bird's eye view, we are in a helicopter above the donkey, it would look kind of like this. You have the cart, you have the donkey pulling this way, its displacement is going that way, you have friction going back. This is the one we're going to use for the work that the donkey is doing. This is the view that is most useful. From the first free body diagram, that more complicated one I drew first, the donkey's force and the displacement appear to be going in the same direction. But we can tell from the top view that there is indeed an angle, angle B, between the force that the donkey is applying and the displacement. So the work done by the donkey is going to be FD cosine of theta, and in this case, the theta is angle B. So we have the force that the donkey is applying, given in the problem, the displacement, also given in the problem, and the angle, angle B, which is the angle that the rope makes, right there. All right, cool. All right, so it's cut off from my picture, but the next thing we want to find is the work done by gravity. And our second free body diagram, the one we used for the work from the donkey, it doesn't even have gravity in it because gravity is going sort of into my screen and displacement is going kind of to my right. So that's not super helpful. But if I look at the first free body diagram, I can see that there is a gravitational component that is opposing the displacement, which is going up the hill. So if I switch over to yellow here for the second part, the work done, the displacement, in this case, is going to be going up the hill. And there's a component of gravity, this x component of gravity, that is opposing that displacement. So right away, I know it's going to be a theta. They're opposing. They're in opposite directions. Okay, the x component and the displacement, one's going to the right, one's going to the left. So I know it's going to be negative work. It's going against the displacement. So we got two different ways to look at this. we can find that yellow arrow, that x component of the gravitational force, and know that that's opposing the displacement and know that that makes it a negative work. Or we can do FD cosine theta. Either way works just fine. I'm going to do it the way that I am most comfortable with, and I'm going to say that the work done by gravity is going to equal the force applied times the displacement, and only look at the component that is opposing the displacement. So I'm going to find FGX. Now FGX is the same as this, which is the opposite of angle A. So FGX, I'll do it up here. FGX is going to equal FG times the sine of angle A. So the work done, I know because FG is to the left and the displacement is to the right, it's going to be negative, and it's going to be FG times the sine of A times the displacement, which is given in the problem. FG is the mass of the cart times 9.8. Mass of the cart is given in the problem. So it's going to be negative m of the cart times g times the sine of angle A times the displacement, which is also given in the problem. That's how you get the work done by gravity. All right, last we're asked to find the work done by the frictional force. And the frictional force is also going to be opposing the motion, so it's going to be negative force of friction times the displacement. But we got to figure out the force of friction. Going back, looking at my free body diagram that I drew, we had gravity going like this, we had the normal force going like that, we had the donkey's force going up, and we had the force of friction going back. We know that force of friction is going to equal mu times the normal force. Well, this is the normal force going up. So we got to figure out the normal force if we're going to figure out the force of friction. Mu is given in the problem. We're given that. It's not accelerating in this free body diagram in the y direction. So whatever the downward component is here is going to equal the upward component, the normal force. So the normal force is going to equal Fgy, which is the y component of gravity. Remember that gravity is equal to m times g, and this was angle, I think angle A. So Fgy is going to equal m times g times the sine of A. And that's going to equal the normal force.
Right.
Oops, that actually, it's the adjacent, right? The adjacent, I should know my trigonometry. It's cosine. Mg cosine A. All right. Just make sure you guys are paying attention. That's all. All right, so now we're going to put all of this stuff together. So this stuff equals the normal force. So I'm going to put that into this friction equation. And then I'm going to put that friction equation into my work equation over here. So work is going to equal negative force of friction, which is mu times the normal force, but the normal force equals mg cosine of angle A, and all of that multiplied by the displacement. And that is how this problem is solved.